Professor, I think you're muted.
Oh, sorry. Whoops. Okay, thanks. Okay. So it's lecture 15. And in the next 3 lectures, we're going to talk about chapter 5, which is about eigenvalues, eigenvectors, and diagonalization. And this is, I think this is very surprising. So up till now, we've been doing the part of linear algebra that is kind of developing this language that has a lot of nice properties that allows you to describe various mathematical and other objects. But in chapter 5, we'll see something that's more than just a language. It's actually a really surprising phenomenon that happens with these objects. And for me, I mean, really, if you show me a matrix, the first question I will ask is, what are the eigenvalues? So for me, this is what really captures the meaning of a matrix. I mean, I'm probably biased by what I work on, but this is very relevant to, if you're a physicist, this is also the first thing you'll ask. So what's the motivation for this? Well, last time we discussed change of coordinates, right? And one consequence of that was that you can represent a given linear transformation from V to V with sorry, I don't know how that happened. So you can represent this relative to many different bases. So we saw an example where if you have 2 different bases of V, then you get 2 different matrices of T with respect to these bases, right? So if you have different bases, you can represent the linear transformation using different matrices. And some of, not all these matrices are equally nice. Last time we saw an example where in one basis, the matrix had a lot of zeros, and another basis it didn't. So some bases yield simpler matrices than others. And this leads us to a deep question, which is given a linear transformation, what is the best basis? So which basis yields the simplest matrix? Okay, so basis conceptually is like a frame of reference or a perspective. And we're saying you can look at this object from many different perspectives. Which perspective gives you the clearest description? And okay, I wrote that this is a deep question. So to see how deep it is, let me show you a clip. So this is a scene from Avengers Endgame. And don't worry, it's not a spoiler. And you'll see that this is like a very important subject. So wait, where did my play? Okay, I'll just play it like this. By the way, is sound being shared? Wait. Yeah, okay. To share sound. Okay. Okay, so I mean, that doesn't really give anything away about the movie, but I have experienced this many times in my life. So you saw what happened, that he did something, he computed an eigenvalue, and when he saw what the eigenvalue was, he totally like flipped out. That has happened to me many times. And hopefully after the end of this chapter, later in life you'll understand why it's so important, but that's what we're going to study. So let me tell you what an eigenvalue is. So to put it in context, so far, we've been concerned, everything we've done is essentially somehow related to a particular type of equation, which is a linear system, which is given a matrix A that's m by n and a vector B. The question was to find a vector x such that ax equals b. Okay, so that's a linear equation. And what we're going to study in chapter 5 is a different kind of equation. This is the second important equation in linear algebra. And here we're given a matrix A that's square, and we're just given a matrix, okay? And the goal is to find a scalar lambda and a vector x such that ax equals lambda x. Okay, so this equation, the variables are both lambda and x. Okay, the only thing that's given is a. And I'm actually multiplying the variables together. So, so this is a nonlinear equation. This is not a linear system. Okay. Now, I'll motivate this in a second. I'll tell you why this is a sensible equation to solve. But eigenvalues and eigenvectors are the solutions of this equation. So let's put a definition. So a non-zero vector, or maybe I'll just say given a matrix A, given a square matrix A, a non-zero vector x in Rn is an eigenvector of A if it satisfies this equation, ax equals lambda x for some scalar lambda. And then this scalar is called the eigenvalue. So this lambda is called the eigenvalue corresponding to x. Okay, so let me show you an example just to make it clear what this means. Let's look at this matrix A. Let's look at the matrix 2, 1, 1, 2. So if you multiply this matrix by, any old vector, let's say you multiply it by E1. So E1 is the vector 1, 0. Then, okay, you just get the first column. And this is not a scalar multiple of E1, right? So this is not an eigenvector. Okay. And geometrically, an eigenvector is a vector which does not change direction when you multiply it by A. Okay. So this is some linear transformation. It takes an input vector and maps it, a vector in R2 and maps it to another vector in R2. And the eigenvector equation is asking, is there a vector that doesn't change direction? So geometrically, an eigenvector doesn't change direction under A. So when you multiply by A, when multiplied by A, let's just put it that way. Okay, so now it's not clear if there's, just looking at this matrix, it's not clear if there is such a vector actually, right? Now I'll tell you how I found this later, but I actually found two vectors that don't change direction when multiplied by this matrix. So let's consider these vectors. Let's look at the vector 1, 1. Well, when you multiply by 1, 1, what do you get? You get 2 plus 1, 1 plus 2 in the entries, which is just 3, 3. So this is 3 times 1, 1. So this is an eigenvector with eigenvalue lambda equals 3, because the scaling factor is 3. So the eigenvalue is the scaling factor. And here's another vector that has this magical property. If you look at the vector 1 minus 1, then, okay, you get 2 minus 1 and 1 minus 2, which is 1 minus 1, which is 1 times minus 1, 1 minus 1. And this is also an eigenvector with lambda equals 1. So I found two vectors that don't change direction when you multiply by A. So there's also always the 0 vector, but we never count the 0 vector. The eigenvector has to be not 0, because 0 is sort of a trivial, boring solution, right? A times 0 is always some number times 0. In fact, any number, right? So the vector has to be non-zero. So these were the two eigenvectors that I found. Now, any questions about this example?
Can you explain again what it means by eigenvectors doesn't change direction when multiplied by A? Is it that like it doesn't change positive or negative sign?
Oh, no. It just means, oh, sorry. It means that, okay, I see. It's allowed to change sign. Okay, good point. So it lies on the same line. Okay. So, so that means AX lies in the span of X. Does that answer the question?
Yeah, that makes sense.
So it doesn't, vectors, we're thinking of vectors as being arrows in the plane. In general, if you apply a linear transformation to a vector, so we multiply a vector by a matrix, it will change direction. It will fall off the span of itself. An eigenvector is one that doesn't change direction in this sense. I mean, in fact, that's what the eigenvector equation is saying, right? Ax equals lambda x is the same thing as saying x is a scalar multiple of ax. Any other question?
I had one question, if that was okay.
Yeah, absolutely.
So for any given square matrix, is there always a non-zero eigenvector associated with it?
It's a great question. I'm going to explain that in a moment. So we're going to study two questions in this lecture. So let me write down the two questions. So one was the question that was just asked, which is given a matrix A that's n by n, how do you find the so how do you find pairs lambda and x such that the eigenvector equation holds? That's the first question. And the second question is, how many solutions are there, right? So given a matrix A, how many solutions lambda x are there? So these are both very interesting questions that we're going to spend the rest of the lecture on. How do you find eigenvalues and eigenvectors, and how many solutions should you expect to have? Okay, any other questions?
Yeah, I was wondering if this is connected in any way to determinants.
It is. It's highly connected to determinants in a way which I will tell you about in a moment. Any other question? Okay, let's study the question of how to find. And so this is sometimes, by the way, called an Eigen Pair. This terminology is not really used in the book, but it's used a lot throughout science because eigenvectors and eigenvalues come in pairs, right? Corresponding to the eigenvector, there's an eigenvalue. And yeah, this only applies to square matrices. This equation doesn't even make sense for rectangular matrices, right? Because if A is not square, then AX is not even the same dimensions as X. Okay, so how do you find eigenvalues and eigenvectors? So it sounds like, according to the definition, it sounds like you should start by looking for the vector, right? But it turns out if you first know the scaling factor, if you first know the eigenvalue, then it's easy to find the eigenvectors. Okay, so remember, we want to find solutions to this, right? And X cannot be 0. So the first observation is, if we knew lambda, if we know the eigenvalue lambda beforehand somehow, it's easy to find the eigenvector. So why is that? Well, AX equals lambda x, that's the equation we want to solve. And suppose we know lambda. This is true if and only if you just rearrange it. AX minus lambda x is equal to 0. That's just the definition. But then this, just by matrix algebra, lambda times x is the same as lambda times identity times x, right? So this is the same as applying the matrix A minus lambda times identity to x equals 0. Any questions about that step? I'm using just properties of matrix algebra here. Okay, but this is equivalent by what we did before the midterm to, yeah, please go ahead.
Oh yeah, why do we need the identity matrix? Couldn't we just leave it as lambda?
Well, we need the identity matrix because we're subtracting something from A, right?
Okay.
And that should be another matrix. So here I'm using the fact that lambda times identity times x is equal to lambda times x. But I want to subtract from A another matrix, right? I can't subtract a number from A. Yeah, good question. Any other question? Okay, so this is equivalent to saying that x is in the null space of A minus lambda I. So A minus lambda I is a shift of A, right? By a multiple of the identity. Now, if I gave you lambda, how would you solve this last problem?
Can we just use row reduction?
Yeah, just use row reduction. Okay, so if you somehow know lambda, then it's easy to find all of the eigenvectors. You just do row reduction and all the non-zero vectors in that subspace. So concretely, what you'll do is you'll use row reduction to find the basis for this. And then that tells you all the eigenvectors, right? So given an eigenvalue, it's easy to find all the eigenvectors. It's just row reduction. It's a linear system. Any questions about this observation?
Can you explain why we need to row reduce? Like, what does row reduction do?
Oh, well, row reduction is something that allows you to solve a linear system, right? And now this a minus lambda I times x equals 0, this is a linear system in the variable x. So if we know lambda means you treat lambda as a constant, right? And so then it's just a linear system. That's all I mean. Does that answer the question?
Yeah, thank you.
So yeah, so of course, lambda is not a constant. We'll get to that later. But if we knew lambda, then we could just do row reduction. However, this little discussion reveals an interesting fact. It reveals that eigenvectors come in subspaces, right? So it reveals that the set of eigenvectors corresponding, so a set of eigenvectors x corresponding to an eigenvalue lambda of A is a subspace. So it forms a subspace of Rn because it's a null space, right? But there's one little edit with the zero vector, right? So after including the zero vector, that's why I use the word forms. Because 0 is never itself an eigenvector, right? This little, observation does tell us something interesting. And so what's the terminology? Is that if A is n by n, lambda is an eigenvalue of A, we use E sub lambda to denote this subspace. So this is the null space of A minus lambda I. Okay, it's a null space, sorry. And that's a subspace, and that's the set of all eigenvectors x such that ax equals lambda x with one more vector, the zero vector. And this is sometimes called an eigenspace. Okay, so given an eigenvalue, it's pretty easy to find the eigenvectors. They're just null spaces of shifts of A. And they form subspaces if you include the zero vector. So let me just illustrate this definition with an example.
Can I ask a question about that definition?
Yes, please.
So does this mean that every lambda does not have a unique, or like every eigenvalue does not have a unique eigenvector? It can have many eigenvectors?
Absolutely. So we just saw that if there's a lambda that's an eigenvalue, the null space could have, well, even if it's one dimensional, first of all, you can multiply x by any number, any non-zero number, and you'll get another eigenvector. But you can even have a two-dimensional subspace of eigenvectors. So I'll show this in the next example. It's a great question.
Okay.
In particular, yes, given lambda, the x is not unique. That's one consequence. So let's look at an example. Let's look at this matrix A, 1, 2, 2. Now, the Okay, so diagonal matrices, it's really easy to compute the eigenvalues. Let's just, here's a fact. Well, I mean, let's just work it out in this example. If you look at A times E1, that's just going to be the first column. That's 1 times E1. A times E2, that's just going to be the second column. That's 2 times E2. A times E3, that's just going to be the third column. That's 2 times E3. So the general fact here is that the eigenvectors of a diagonal matrix are just the standard basis. And the corresponding eigenvalues are the diagonal entries. Okay. So in this case, we computed, 3 different solutions to the eigenvector equation. These are all 3 are different. But really, the right way to think about them is in eigenspaces, right? So what are the eigenvalues? Well, there are only 2 eigenvalues that came out here, 1 and 2. And now we can compute the eigenspaces. So E1 is going to be the null space of A minus 1 times identity. So that's going to be 1 minus 1, 2 minus 1, 2 minus 1. So this matrix is A minus 1 times identity, right? Okay, that's not very good notation, but you can see. And this is the null space of the matrix 0, 1, 1, which is a span of E1. And indeed, every non-zero vector in the subspace is an eigenvector of A. I could have done 2E1, right? Or 3E1 or minus 2E1. So really the right way to think about the solutions is it's this span of E1. And of course, you don't use the 0 vector doesn't count. And then there's another eigenspace, E2, corresponding to, remember, there are 2 eigenvalues. E2 is a null space of A minus 2 times identity, which is the null space of this matrix. So 1 minus 2, 2 minus 2, 2 minus 2, which is a null space of this matrix, minus 1, 0, 0, which you can easily see. It's already essentially in reduced to echelon form, is the span of E2 and E3. So in this matrix, there are 2 eigenvalues. I mean, I haven't proven those are all of them. I'll do that in a moment. But there are actually only 2 eigenvalues, 1 and 2. And there are 2 eigenspaces. The dimension of one of them is 1. So up to scaling, there's a unique eigenvector corresponding to the eigenvalue 1, right? So this is the lambda equals 1 eigenvalue. But for the lambda equals 2 eigenvalue, there's actually a whole 2-dimensional subspace of eigenvectors. So can anyone tell me an eigenvector that's not E2 or E3?
0, 1, 1.
Oh, sorry.
Sorry.
Yeah, thank you. So for example, this E2 contains many other vectors, right? It contains, for example, the vector 0, 1, 1. That's also an eigenvector. And what is this saying? It's saying everybody in this 2-dimensional subspace, A does something very simple to all those vectors. It just stretches them by 2. It doesn't change the direction, right? So geometrically, A stretches every vector in E2 by a factor of 2 without changing the direction. And in E1, it stretches everything by a factor of 1, so it doesn't change them at all. And this is special, right? If I plug in a vector that's not in one of these subspaces, it will change the direction. Right? If I plug in the vector 1, 1, 1, that's not in either of these subspaces, that will have its direction changed. Okay, so these eigenspaces are very special.
I had a question.
Mm-hmm.
Is it possible for an A not to have an eigenvector?
Great question. We'll get to that in a moment.
Okay.
So right now, again, I'm still doing an example, right? I still haven't told you. I've told you how to find eigenvectors given the eigenvalues. I haven't told you how to find the eigenvalues. But okay. However, your question was, is it possible for A not to have an eigenvector? The answer is yes. But if something is an eigenvalue, then it has to have an eigenvector, right? Because an eigenvalue, by definition, you can't have an eigenvalue without an eigenvector. So if A has an eigenvalue, then it has an eigenvector. Any more questions? Okay, so we've kind of just sort of kicked the can a little down the road here. This is how to find eigenvectors given the eigenvalues, but how do you find the eigenvalues, right? We don't know this lambda, so now we write. Okay, so there's a key idea in this, which is again a short idea. Okay. Well, okay, so lambda is an eigenvalue of A. Well, what's the definition? The definition is that AX equals lambda X for some non-zero vector X. That's the definition. And we just noticed that that's equivalent to some statement about the null space, right? This is equivalent to saying A minus lambda times identity X equals 0 for some X not equal to 0. But now we're going to remember the invertible matrix theorem, right? So if you have a non-zero vector X, so that A minus lambda I times X is equal to 0, what does that tell you about A minus lambda I?
It's non-invertible because we have a we have a trivial solution, I guess.
That's right. It's not invertible. So this is equivalent to saying A minus lambda I is not invertible. And now the invertible matrix theorem gives you like 30 different equivalent conditions for this, right? But one of them is particularly useful because we're trying to find a value of lambda such that this is not invertible. And this is where it's very handy to have a formula that decides whether a matrix is invertible, and that's given by the determinant. Okay, so that's by the invertible matrix theorem.
Professor?
Yep.
Could you repeat why it's not invertible?
Well, I just followed the definitions, right? Lambda is an eigenvalue if and only if A minus lambda X equals 0. This is by the invertible matrix theorem, right? So if there's if AX equals 0 has a non-trivial solution, in this case, A is A minus lambda I, right? If A minus lambda X has equals 0 has a non-trivial solution, then A minus lambda I is not invertible.
Okay, got it. Thank you.
Okay, so this is kind of interesting because this last quantity here, this is an equation in the variable lambda, right? If I were to expand this out all the way, I would get some equation involving the variable lambda. And then I could solve that equation and find the eigenvalues. Okay, so what's the sort of conclusion? The eigenvalues of A are the roots of, or are the solutions. Well, okay, I'll just say are the roots of the following polynomial, chi sub A of t equals det of A minus ti, where this t is a variable. Okay, so roots. Well, okay, are the roots of this thing, which is a polynomial. I'll prove that in a moment. And this is called the characteristic polynomial. Okay, so this is always a polynomial in the variable t. I've changed the variable from lambda to t because I was using lambda to refer to specific eigenvalues, and I just want to emphasize that this is a variable. It's not a constant. And the equation, the equation setting this to be equal to 0 is called the characteristic equation. Okay, so the eigenvalues are solutions of some equation, which is not a linear equation, right? So let me demonstrate this with an example. This might seem a little abstract, but the point of this slide is that the eigenvalues correspond to roots of some polynomial, which is a characteristic polynomial. So let me do it with an example. Let's do our example from the beginning of the lecture where I just produced eigenvectors out of thin air. Okay. So now the point is that what we just observed is that lambda is an eigenvalue of A if and only if determinant of A minus lambda I equals 0, right? That's what we wrote on the previous slide. So let's calculate the characteristic polynomial. So characteristic polynomial of A in the variable t is determinant of A minus ti. So 2, 1, 1, 2, that's A minus t times identity. Now t times identity is this matrix. So this is the matrix A minus t times identity. So this is the characteristic polynomial. And now, okay, so this is some matrix arithmetic. 2 minus t, 1, 1, 2 minus t. And now this is a bit of a twist. So you're used to calculating determinants of matrices that have numbers in them, right? But now you have a determinant of a matrix that has variables in it. But the same rule applies. The same definition applies. And the useful definition in this case is the recursive definition. For 2 by 2 anyway, it's easy. This is 2 minus t times 2 minus t minus 1. So this is the, I guess, definition of determinant. And if you work this out, this is t squared minus 4t plus plus 3. And so what's the characteristic equation? Well, it's you set this to be 0. And well, we know how to solve that, right? So 4 plus or minus square root 16 minus 4ac, that's 12 over 2. So that's 4 plus or minus 2 divided by 2. That's 3 or 1. That's just a quadratic equation, right? So what's the conclusion? The eigenvalues are 1 or 3. Okay, and that's all of them. That's all of the eigenvalues, right? Because everything is if and only if here, right? Lambda is an eigenvalue if and only if it's a root of the characteristic polynomial. And the roots are exactly 3 and 1. And this is consistent. Well, I mean, let's just complete. This is consistent with what we did earlier in the lecture, right? In this example, remember these numbers were 3 and 1. So it's not a coincidence. And we just showed that those are all the eigenvalues. Okay. People are asking very good questions in the chat. I'll be getting to them in the next slide. If you have questions about this slide so far, please ask.
Why does the characteristic equation use t instead of lambda? Is it just convention, or is there any particular?
It's my convention. People use. I'm using t to emphasize that it's a variable. So because we used lambda previously to talk about like a specific eigenvalue, like here, right? I'm just using t to emphasize that it's a variable. If you prefer to use lambda, that's fine too.
Thank you.
Yep. So I'm using lambda to denote specific eigenvalues and t to denote the variable. Okay, but now this is good, right? Because remember, given the eigenvalues, it was pretty easy to find the eigenvectors. You just do row reduction, right? The eigenspaces are just null spaces. So this was step 1. And now, so let's call this step 1, finding the eigenvalues. And now step 2 is, well, we know the eigenvalues, so now we know how to find the eigenspaces. E1 is the null space of a minus lambda I, right? So this will be 2 minus 1, 1, 1, 2 minus 1, which is the null space of the matrix 1, 1, 1, 1, which is the span of the vector 1 minus 1. And E3, which is the other eigenvalue, is the null space of the matrix 2 minus 3, 1, 1, 2 minus 3, which is the null space of the matrix minus 1, 1, 1, minus 1, which is the span of this vector. I mean, I'm skipping some row reduction steps here because we know how to do row reduction. I'm not emphasizing it anymore. But this is the same as what we did. This is exactly the same as what I showed you on the first slide, right? These special vectors 1, 1, and 1 minus 1. So this method worked in this example. So this is same as on the first slide. So if I call these vectors, let's say v1 and v2, then you have the property that a times v1 is equal to 1 times v1, and a times v2 is equal to 3 times v2. And we checked that already on the first slide. So how to find eigenvalues and eigenvectors is not that complicated. It's a two-step algorithm, which I will now summarize. But any questions on the example first? So yeah, just to clarify, this is the matrix A minus 1 times identity. And this is the matrix A minus 3 times identity.
Professor,
Mm-hmm.
it would not be correct to say that the eigenvectors for A are just those vectors 1, -1, and 1, 1, right? It's like all of the different vectors that you can span with them, right? So you can't just say that there are two, there are infinite.
There are infinitely many, yeah. But it's not all it's not the vectors you can span with both of those, right? So a linear combination of eigenvectors is not an eigenvector. It's an important fact, right? So there are infinitely many in each of the spans. That's true.
Right.
But yeah, you can't add eigenvalues from different eigenvectors.
Okay, thanks.
Yeah.
If we find an eigenvalue, then this means that the null space is non-trivial. Or
Correct.
I mean, okay.
Because look at this example, right? If something's an eigenvalue, one of the things in this list of equivalences is that the null space is non-trivial.
Okay.
Namely the second equation up here. So you're right. Right? I mean, we said it before also. Lambda is an eigenvalue if and only if the null space is non-trivial. Any other question?
So can we just conclude that the reason why A minus lambda times identity matrix is because we need non-trivial solution?
Yeah. So, you know, we chose lambda equals 1 because we knew that the null space was going to be non-empty, right? We chose the lambda, so A minus lambda I is not invertible. So yeah. Okay, so let me summarize what we just did. So general algorithm. So given an n by n matrix, there are two steps. Step 1 is find all the roots of the characteristic equation. And then this will give you the eigenvalues. And then step 2, now that you know the eigenvalues, you just do row reduction. So for each eigenvalue lambda, find a basis of the null space.
Quick question.
Using row reduction. Yeah.
So for the final roots part, is it possible to get imaginary roots or no?
Absolutely possible, but we will not discuss it until next week since you know, some people are maybe not so familiar with complex numbers. But yeah, right now
Okay.
we've defined eigenvalues as being real. Next week we'll look at imaginary also. Okay, so let me demonstrate the algorithm on a more complicated example. Okay, so let's say find all real roots for now. Imagine we'll deal with imaginary roots next week. Okay, so let me work out an example just to illustrate the algorithm. So let's say I give you a matrix A. Sorry, it's getting a little dark over here. Let me just turn on the light. So here's a fairly involved matrix, which pretty impossible to find the eigenvalues just by eyeballing it. So it's a 3 by 3 matrix. So what's step one? Well, I need to find the roots of the characteristic polynomial, so I need to find the characteristic polynomial. So let's find it. So this is a determinant of a 3 by 3 matrix, right? Now the matrix is A minus T identity. So on the diagonals, I pick up a T, 1 minus T, 3, 3, minus 3, minus 5, minus T, minus 3, 3, 3, 1 minus T. And now I have to expand this. I have to find this. I have to find the characteristic polynomial. Okay. So now I'm going to use the recursive formula, right? Where, I pick the first row, let's say, and then I reduce it to some 2 by 2 determinants, which we've done before the midterm. So you get this is 1 minus T times the determinant of this little matrix. Then you get minus 3. You have these alternating signs. Now you have minus 3, 3, 1 minus T. Plus 3, minus 3, minus 5, minus T, 3, 3. And now, okay, you do one more time. So you get that this is 1 minus T. And now here you get minus 5 minus T times 1 minus T plus 9 minus 3. Here you get minus 3, 1 minus T plus 9. And here you get minus 9, I guess. I guess minus 3 times minus 5 minus T. And if you do all this algebra, you get this minus T cubed minus 3T squared plus 4. And now you need to find the roots of this. And as somebody mentioned, now, okay, in this, I don't expect you to know the formula for finding roots of a cubic polynomial. There is a formula. In this case, I happen to know it, so I'll just tell you that you can factor this as follows. This is equal to minus T minus 1 times T plus 2 squared. Okay. So in general, I'll always give you polynomials where it's easy to factor them. This one, it wasn't that easy, but okay. In general, this can be a somewhat involved step, but anyway, you can do it. So this one factorizes in this way. And now the characteristic equation is this is equal to 0, right? And so now what are the roots?
1 and negative 2.
1 and negative 2. You can read it off the factors, right? So the roots are 1 and negative 2. And I'm going to distinguish between the negative 2 and the 1 by the number of times that factor appears in the factorization. So this appears twice. And this appears once. And there's some terminology for this, which I'll introduce here. The number of times T minus lambda appears as a factor of the characteristic polynomial, chi A of T is called the algebraic multiplicity of the eigenvalue lambda. So this has algebraic multiplicity 1. This has algebraic multiplicity too. Okay. So this was just step one. I found the eigenvalues. So the eigenvalues are 1 and -2. And actually, now I have this new, by looking at the number of times a factor appears, I also, I haven't told you why this terminology is interesting in a moment yet, but I'll tell you in a moment. But anyway, I found the eigenvalues. So any questions about step one for this matrix? Okay, let's do step two. Now that we have the eigenvalues, it's kind of easy. You just find the null spaces. So step two. Well, the eigenspace corresponding to 1 is the null space of A minus identity, which is the null space of this matrix. So 1 minus 1, 3, 3. 3, 3, 1 minus 1. So subtract 1s on the diagonal. And you do some row reduction, which I'm going to skip here. You get that this is the span of this vector 1 minus 1, 1. So that's the eigenvector with eigenvalue 1. And you can check that indeed it's the case. And the eigenspace corresponding to -2 is the null space of A plus 2 times identity. And if you do the same kind of reasoning and you do row reduction, which I will skip because that's not a new thing, you get that this is a span of these vectors. And I should say, the exact bases are not unique, right? Because you can have many different bases for a vector space. But these are some bases that you get if you do the method of finding a basis of a null space that we discussed earlier. Why is there no T next to the I in the first line? Which line are you referring to? Yeah, there is. It's just 1. So that's the algorithm. And that concludes this section, which is how to find eigenvalues and eigenvectors. These compute roots of the characteristic polynomial and then do row reduction. Okay, people are asking excellent questions like what does algebraic multiplicity have to do with the dimension of the eigenspace? So we'll get to that in a moment. In this case, the algebraic multiplicities were 1 and 2. The dimensions of the eigenspace were also 1 and 2. Is that a coincidence? Well, let's find out in part 2 of the lecture, which is how many solutions are there? So how many eigenvalues and eigenvectors are there? Let's deal with eigenvalues first, right? So the key here is the following fact. It's that let's see what the characteristic polynomial is like, right? So it's a determinant of some potentially very big matrix, which has some entries, and the diagonal entries have minus t's in them, right? And the rest could be anything. Now, according to the recursive formula, you can always compute this determinant by just, expanding along a row, right? So according to the recursive formula, if you really zoom out and see what the recursive formula does, it tells you that this, whatever you get out here, this is a sum of products of groups of n entries of this matrix. So I won't, it's a very specific thing, but you'll believe me that if you do the recursive algorithm, you do at most one multiplication and every step you reduce the size of the determinant, and you do that at n times, right? So in the end, whatever you get, it's some sum of products of n entries in this thing. But notice that there are only n t's in here, right? And these entries are always distinct. So if you multiply all these things together, what you get is a polynomial of degree n. In the variable t. Okay, so this is, it's a fact, it's a true fact. What I told you is a sketch of a proof, which is almost a full proof. You just have to believe this fact that when you do this expansion, you get a sum of products of n entries of this thing at a time. And now, as somebody asked earlier, there's a famous theorem called the fundamental theorem of algebra. Which was proven by Gauss when he was 18 years old, which says if you have a polynomial of degree n, it has at most n real roots. Has at most n real roots and exactly n complex roots, but we'll deal with that later. Okay, so root is a number with the property that p of lambda equals 0. And so this tells us that you can never have more than n eigenvalues countered with multiplicity, right? Because the characteristic polynomial is a polynomial of degree n. A polynomial of degree n has at most n real roots. So what's the consequence? An n by n matrix has at most n real eigenvalues where you count with multiplicity. With algebraic multiplicity. Okay, so you can never have more than n eigenvalues. So a 2 by 2 matrix can never have more than 2 eigenvalues. So that's how we know that in that example previously, in this example, we found 2 eigenvalues, that's all of them. In this example, we found 2 eigenvalues, but when you count with multiplicity, we found 3 eigenvalues, and that's all of them by the fundamental theorem of algebra. So these must be all the eigenvalues. So this tells us how many eigenvalues there are. Any questions about this?
Is this a proof for the fundamental theorem of algebra, or is that just a statement?
No, that's just a statement. So this is proven by Gauss, and we will not prove. It's kind of beyond the scope of the course. If you want to see the proof of this, take Math 185, which I highly recommend. So we're just bringing this statement from somewhere else. But I guess you must be familiar with this fact from day-to-day life, even if you haven't seen a proof. Any more questions? I should remark that there are matrices which don't have any real eigenvalues, right? So here's an example. Consider this matrix A equals 0, 1, minus 1, 0. And this corresponds to rotating a vector by pi over 2 radians, right? Now, what's the characteristic polynomial? Well, it's the determinant of this. which is t squared plus 1, which has no real roots. So this has no real eigenvalues. And that makes sense, right? Because is there any direction which is fixed when you rotate it by pi by 2? No, right? There's no direction in the plane such that when you rotate it, you get back the same direction. But we will discuss complex eigenvalues later. So we'll later expand our definition to include complex eigenvalues. But don't worry about that right now. I don't want to scare you with complex numbers yet. So any questions about this? So in this case, there are really 0 real eigenvalues. So you can have, you can have less than n real eigenvalues. So that's it for counting eigenvalues. What about eigenvectors? That's actually more interesting and quite a bit more subtle. Any questions about this?
So we can only know at most how many eigenvalue we can have, then, but not like the exactly how many. Okay.
The only way to know exactly how many real eigenvalues you have is by actually solving the characteristic equation and seeing how many solutions you get.
Okay, thank you.
Okay, now what about eigenvectors? How many eigenvectors can you have? Now, you shouldn't ask how many eigenvectors, right? Already in this example, we have infinitely many eigenvectors, right? Like here already you have span of a vector, so you have infinitely many. Was somebody about to say something?
Oh no, I was about to say infinitely many.
Correct, infinitely many. So to really ask the interesting question, you shouldn't ask how many vectors, just how many linearly independent eigenvectors. How many linearly independent eigenvectors? Well, can anybody give me, I don't know, some bound on how many? Could you have infinitely many linearly independent eigenvectors? So for an n-bind matrix.
I don't think we can have more eigenvectors than the number of eigenvalues, right?
That's actually not true.
Oh.
We'll look at that in a, I mean, well, it's not true because the identity matrix, right? This has one eigenvalue, but it has actually n linearly independent eigenvectors.
Yeah.
So it will be n.
Yeah, n is sort of a easy bound. So a preliminary bound is at most n because they live in Rn, right? Since the eigenvectors are in Rn. So this is the whatever too many vectors theorem, right? You can't have more linearly independent vectors than the dimension. Okay, so at most n. But we're going to be really interested in the question of when do you have exactly n linearly independent eigenvectors? This is going to be the key to answering the deep question at the beginning of the lecture. Okay, so important question. When are there exactly n linearly independent? Okay, so in general, there's no sort of if and only if condition for this. Okay, so this is maybe the first thing in the course where we can't say this is true if and only if some simple thing happens. It's not that easy to check. So what I'm going to do instead is tell you two sufficient conditions which come up a lot and which are very important. So let me state two important theorems. So here's a theorem. The theorem says if you take eigenvectors that come from different eigenvalues, they're always linearly independent. Okay, so if AV1 equals lambda 1 V1 all the way up to AVK equals lambda K VK for distinct lambda 1 through lambda K, and these VIs are not equal to 0. So if you have eigenvalues corresponding to distinct eigenvectors corresponding to distinct eigenvalues, then they must be linearly independent. Okay. Now the proof is not hard, but I don't want to, this is not a really proof-oriented class. So the proof is in the book. It should be understandable given what we've done so far. It's not very hard. It's a little bit slicker than what we've done. But I won't cover it in lecture. You can just read it in the book. You should read it and ask me about it if it doesn't make sense to you. But this is something that comes up all the time. If the eigenvalues are distinct, then the eigenvectors are linearly independent. So what's a consequence of this? Is that if you have n distinct eigenvalues and distinct eigenvalues, then it has n linearly independent eigenvectors. Okay, so distinct eigenvalues implies enough linearly independent eigenvectors. Now, there's an if-then statement, right? It's a one-directional arrow. If the eigenvalues are distinct, then the eigenvectors are linearly independent. The other direction is not true. Why is the other direction not true? Anybody think of an example?
Because a or like you can have more than two linearly independent. Wait, let me think about the statement real quick.
Isn't the example that you wrote on the page up at the top a counterexample?
Exactly, the identity. The identity only has one distinct eigenvalue, but it does have n linearly independent eigenvectors. So this is a one-directional statement. If the eigenvalues are distinct, then the eigenvectors are linearly independent. Still very useful statement.
This only works for exactly n. Like if A equals n by n, right?
No, so the theorem works for any k, right? If you have you can apply it in cases where you only have like less than n eigenvalues as well. You'll still get a bunch of linearly independent eigenvectors. But the consequence is the case k equals n. You're right. Right? If you have n distinct eigenvalues, then the corresponding eigenvectors are linearly independent. Okay. Now there's another sufficient condition that comes up a lot, and let me just state it. Okay, so this is a wait, do people have more questions about this? I'm seeing some questions in the chat that I'm not fully understanding. Anybody want to ask? Okay, let me just state, yeah, go ahead.
Sorry. So what do you mean by the corresponding eigenvectors?
Well, so every eigenvalue has at least one eigenvector, right?
Yeah.
So I mean that if you have n distinct eigenvalues, then you have at least n eigenvectors, right? So you can choose one eigenvector for each eigenvalue.
Oh, okay.
Then those have to be linearly independent.
Mm-hmm.
And you can never have more than n, right? So that's a there are no other eigenvectors after that.
Mm-hmm. Yeah. Thank you.
Okay, so the other sufficient condition, or the other theorem, which we won't prove, this is proven in Math 110, which was somebody asked this very good question earlier. So if lambda is an eigenvalue of A, then the dimension of the eigenspace corresponding to that eigenvalue is at least 1. That's just a definition, right? But it is at most the algebraic multiplicity in the characteristic polynomial. We won't prove this. This is true. It's a beautiful theorem. But what it says is that this pattern you saw in these examples is not a coincidence, right? Like in this example, or in this 3×3 example, the algebraic multiplicities were 1 and 2. And the dimensions of the eigenspaces were 1 and 2. So this is a fact. It is beyond the scope of this course to prove. This number is often called the geometric multiplicity. Okay, so that's another bound on the number of eigenvectors. Inside each eigenspace, you can, I find this quite magical. You can tell something about the dimension of the eigenspace, which is a fact in linear algebra, by looking at the number of times t minus lambda appears as a factor of the characteristic polynomial, which is a fact in algebra, not linear algebra. Okay, so this, I mean, maybe I'll illustrate this, well, or, okay, so what's one, I guess, consequence of this? I mean, it's not really a, yeah, okay. So it's a consequence of this and the previous theorem. So if lambda 1 through lambda k are eigenvalues of A, and the sum of the dimensions of the eigenspaces is equal to n, then the union of bases of the E lambda i's are linearly independent. Okay, so this is what this is saying is that even if you don't have distinct eigenvalues, if your geometric multiplicities add up to n, then you have also, again, n linearly independent eigenvectors. And this is the case we're going to be most interested in, right? When do you have n linearly independent eigenvectors? In this course, we're not really going to care that much about, I mean, you know, in terms of applications, about cases where there are fewer than n linearly independent eigenvectors. So this is another sufficient condition to have n linearly independent eigenvectors. And I mean, yeah, so maybe instead of calling these consequences, let me call these sufficient conditions, right? So sufficient condition 1. Number 1, and this is sufficient condition number 2 for having n linearly independent eigenvectors. And I should mention that, you know, this doesn't always happen, right? So let me just show you an interesting example. If you just look at the matrix A equals 2, 2, 2, 1, then okay, its characteristic polynomial is just determinant of 2 minus t, 2 minus t, 2 minus t, 1. It's just 2 minus t cubed. So there's one eigenvalue, 2 with algebraic multiplicity equal to 3, because it appears 3 times as a factor. But what's the geometric multiplicity? Well, E2 is a null space of A minus 2i, which is a null space of this matrix 0, 0, 0, 1, which is the span of, I believe, E1 and E3. And so the dimension of this is actually 2, which is less than 3. So this can happen. Anyway, that's it for today's lecture, and I guess see you next time.
Thank you.
Yep, thanks. Any questions?
Thank you.
Wait, can you repeat like the
Thank
last
you.
one you said? Like 2 can't be what?
Oh, the last thing I said is in this case, the geometric multiplicity is strictly less than the algebraic multiplicity. I think that's what I said, right?
Okay, thank you.
So does that mean the algebraic multiplicity always has to add up to n? Like all the algebraic multiplicities, but the geometric multiplicity doesn't have to?
Exactly. So right now we've defined, right now we're only looking at real eigenvalues. So in real eigenvalues, the algebraic multiplicity could even just be 0. In this case, the algebraic multiplicity is 0, right?
Oh yeah.
But
So
when we move
it
to
doesn't matter.
complex, which we will do next week, indeed, the algebraic multiplicities will always add up to n, because this fundamental theorem of algebra says that exactly n complex roots.
Okay.
So you're right. You're anticipating what we'll do next week, that the sum of the algebraic multiplicities will always be n if you allow complex eigenvalues. But the sum of the geometric multiplicities could be less. For example, in this matrix.
Will it be n if there are eigenvalues, like the sum of the algebraic multiplicity?
Yeah. So look at this example, right? So there is an eigenvalue, right?
Yeah.
But
And
there still aren't enough eigenvectors. There are only 2 linearly independent eigenvectors.
but that's geometric multiplicity, right?
Yeah, but that's what Jim. Maybe I misunderstood the question.
Oh, well, I meant to ask, like, isn't algebraic multiplicity always going to add up to n if we have eigenvalues?
Oh yeah. Oh, you mean if all the eigenvalues are real? Yes, you're right.
Yeah.
So mark if all roots of the characteristic polynomial are real, then the sum of the algebraic multiplicities is equal to n. And this will always be this will be true in general if we allow complex root. But we'll do that next week.
Wait, if they're real, then can we include 0? No, right?
Oh yeah. 0 is perfectly valid eigenvalue. 0 is a perfectly valid. Remember, the thing that can't be 0 is the eigenvector. The eigenvalue can be 0. There's no problem with that.
Okay.
Professor, can you explain like E2 equals null of A minus 21? Where did you get the 21?
Oh, it's not 21. It's 2 times identity. Sorry.
Okay, thank you.
Yeah. Sorry.
Makes more sense.
Okay.
Does the number of distinct multiplicities tell you anything?
The number of distinct multiplicities. Yeah, it does tell you something, but it tells you something that's kind of beyond the scope of the course. So if you're interested in that, then I mean, it's a subject of like representation theory and some other subjects. It does tell you something. Maybe I'll talk a little bit in the next lecture about what it says in the context of this course.
All right, thank you.
Yep.
Also, where does the word eigen come from?
That's a good question. So the word eigen it's a German word, So eigenvector, I believe, means own in German.
Mm-hmm.
So it's like your own vector. I don't know. I mean, in some sense, these are the most important vectors associated with the matrix. And maybe that's why this word was used.
Who discovered them?
I don't know. It's a good question. I don't know. It's not associated with any person's name.
Thank you.
Yep.
So just to clarify, there can be a finite amount of eigenvalues, and if there are like an X amount of eigenvalues, then there will be an X amount of linearly independent, or there'll be an X amount of linearly independent eigenvectors.
No. So the amount of linearly independent eigenvectors is at most.
Oh, okay.
Oh, I see. Are you talking about distinct eigenvalues or just eigenvalues?
Oh no, I meant distinct eigenvalues.
Oh yeah. No, then you're right. Yeah. Then by this theorem, if you have k distinct eigenvalues, then you have k linearly independent eigenvectors. That is true.
But in terms of like counting the number of eigenvectors that exists, assuming that we have eigenvalues, there's like an infinite amount, right? Because we're looking at the entire line.
That's right. That's right. Eigenvectors appear in these eigenspaces. So technically, I mean, if you're literally counting them, there are infinitely many.
I also had a slightly, a bit of a less technical question, more of a general sort of thing. So I find that I'm able to do the computational work that is needed, but I find a bit